Welcome back. So we're talking about computing some of these least squares solutions, and one of the things that comes up frequently is eigenvalue decompositions. And we have worked through how to look at eigenvalues, or compute eigenvalues if you have a 2 by 2 matrix that's symmetric, and that's pretty easy. But you can imagine that beyond that it starts to get trickier. And there are many ways to compute eigenvalues, but this is just one that can be used and is useful, and I find it kind of interesting. So we can compute eigenvalues based on power computations. Now this is an iterative way to compute eigenvalues, but it's fun to do in MATLAB. Try this out and see how it works. Okay, assume we have some matrix A. We are going to go through a set of iterations. The first thing we're going to do is let Q naught be an arbitrary vector in Rn. Okay, and we're also going to define and restrict the norm, the 2 norm of Q naught to be 1. Okay, so then we will say zk is equal to a q k minus 1, and then q k will be equal to zk over the norm of zk, so we'll normalize this. And then gamma k will be equal to qk transpose a qk. And then we'll iterate for k's 1, 2, and so forth. So, what's going on here? Well, if Q naught is not orthogonal to V1, and V1, this is the eigenvector of A with the largest eigenvalue, lambda 1, where lambda 1 is larger than all the rest of the eigenvalues. Okay, so how does this seem to work? As k gets large, we have that qk goes to V1, I'm sorry, and gamma k goes to lambda 1. So we won't go through a detailed proof of how this works, but we can go through some little demonstration of what's going on here. First, when we first choose our QK, or I'm sorry, our Q0, we assume that Q0 is equal to some linear combination of all of the eigenvectors of A, since they form an ortho basis for A. And based on the fact that, look at this, we have back up here at our iterative steps, we're just bouncing back and forth between step 1 and step 2 with zk is equal to A times the previous Q, and then we normalize it, and then we multiply it by A and normalize it, and multiply it by A and normalize it, and this continues until we decide to stop. And because of that, we have that QK is equal to A to the K of Q naught all over that normalized. We can combine those two things to show that we have QK equal to alpha. Okay, now we have A to the K times Q naught. Well, A to the K times V1 is going to be lambda 1 to the K times V1. And then we'll get alpha 2 times lambda 2 raised to the K times V2. All the way up to alpha n lambda n to the K times Vn. And then we normalize that. So we'll get the same. Here we get alpha 1 squared lambda 1 to the 2k plus alpha 2 squared lambda 2 to the 2k all up to alpha n squared lambda n to the 2k, and we take the square root to find the norm. So that's it. And once again, we assume that we have everything sorted like usual in descending values. Well, if lambda 1 is the largest eigenvalue, then this term dominates. As k gets large. So we have that QK is approximately equal to alpha 1 lambda 1 to the k V1 over the square root of alpha 1 squared lambda 1 to the 2k, and so that is just going to equal V1. So we run through these iterations, and essentially all the other terms disappear. So how do we get lambda 1? Well, this isn't too bad. We know that V1 transpose A V1 is just equal to lambda 1, because A times V1 is equal to lambda V1. The lambda comes out, and the V1 transpose times V1 is equal to 1. And so there we are. We have our two solutions. So you can try this out in MATLAB and find that you can get the largest eigenvalue, and it doesn't usually take that many iterations unless your eigenvalues are all very close to each other. We can continue this to find the next. How would we find the next one? Well, to find the next eigenvalue, we have to choose a new eigenvalue, or a new initial vector. Find lambda 2. Choose a new Q naught. I'll just say a new Q naught. I don't know what notation we put there. But this has got to be equal to alpha 2 V2 plus alpha 3 V3 plus all the way up to alpha n Vn. In other words, we have to take off that first vector. Well, due to numeric problems, it might occasionally crop back in. And so we might want to double check now and then as we do the process. But essentially this would be, let's go ahead and call this tilde. So Q naught tilde would be equal to Q naught minus the projection of Q naught onto our normalized V1 that we've already calculated. So this would be Q naught transpose V1 times V1, and that will get us a good starting place. We may have to occasionally redo this to the step of removing V1 in Q tilde K to avoid problems with round off. So we can do this and find the top however many eigenvalues we want to find by just repeating this process. If there's a large spread in eigenvalues, this orthogonalization step may need to be performed slightly more often.